This senior design project focused on the conceptual design of a suborbital space Trojan vehicle. The vehicle design must be a single-stage, rocket-powered, reusable wing-body vehicle that takes off and lands horizontally. The vehicle must reach an altitude of 100 kilometers while not exceeding 3 Gs of acceleration during ascent and 5 Gs during descent, while carrying 6 passengers. The synthesis process chosen to design this vehicle is hypersonic convergence. This process utilizes a method that keeps the performance of the vehicle constant while varying other parameters such as the slenderness ratio to build a solution space. This solution space is then passed through geometry where it is reduced based on the vehicle geometry chosen. Finally, a disciplinary analysis is performed along the vehicle's flight path to determine if the vehicle is capable of completing the mission in a cost-effective and safe manner. If it can, then it remains as part of the final solution space that the selected vehicle is chosen from.
Geometry has developed a database of geometric data for several space planes to better the team's understanding of these sorts of geometries and cabin layouts, and has developed a code to sweep through fuselage and wing geometries to converge to a solution space for the mission profile.
The propulsion discipline is in charge of making sure that thrust requirements are met during each flight phase of the mission and selecting an engine based on their industrial capabilities. The rocket performance will be measured by obtaining the specific impulse, thrust available, and final mass ratio of the system.
Weights and Balance has developed a methodology for performing weight and center of gravity estimations given a particular geometry to project empty weight, takeoff gross weight, and other relevant weights, and has researched proper landing gear configurations for the specified mission profile.
The aerodynamic discipline conducted a literature review to design a methodology for calculating the aerodynamic parameters, including lift and drag, for further analysis of the configuration evaluation phase of the hypersonic convergence process.
The aerothermal discipline is in charge of operating in the boost phase and re-entry phase of flight, where heating effects are deemed to be the highest. The main parameters that are calculated are surface temperatures of the vehicle and heat flux values. These aerothermal calculations will then be used to size the thermal protection system and choose a material that will be able to withstand extreme temperatures while reducing overall weight and cost of the vehicle.
The trajectory and performance discipline was responsible for determining the optimum flight trajectory and the associated required velocities and thrusts to execute that trajectory during both the ascent and descent phases. Takeoff field length determination helped size the wing, while field fraction was calculated to determine aircraft range.
Static stability outputs for the stability and control discipline are the pitching, yaw, and rolling moments of the vehicle. Control outputs will be the minimum surface areas needed in order to properly trim the vehicle and pitch the vehicle for takeoff. For the microgravity, rocket thrusters were analyzed and chosen based on minimum thrust force needed and fuel needed for the time spent.
A market analysis is made to ensure that there is enough demand for the vehicle. Once that is confirmed, a cost analysis is performed for vehicle configuration to ensure that the vehicle is financially feasible for the team and affordable for the projected market. The development, production, and operating cost values are calculated and verified using two different processes. This allows for iterations to be made so the most competitive vehicle that still achieves the mission is selected.
The goal of the safety discipline is to ensure each discipline abides by the FAA's Commercial Space Transportation Safety Guidelines. The safety analysis of spaceship UTA includes determining the vehicle's ability to carry out the mission while ensuring that the passengers, crew, and environment are not in harm's way during any of the vehicle's flight phases by following the Part 450 streamlined licensing process.
So far, a set of solution spaces has been created for each vehicle, and a final solution space is in the process of being produced. Based on the current state of the final solution space, the vehicle chosen will likely have a planform area of under 50 meters squared and a takeoff gross weight of under 10,000 kilograms.